going?
It's going.
Hello, good morning, ladies and gentlemen. Our project is the development of a propane ignition system for the investigation of optimal ignition parameters. I'm Peter Jing, and my teammate is Bana Bejelin and Anisha Kumar. Our industrial supervisors are Shane and Mark Hugel from BL Tech Limited, and our academic supervisor is Craig Bakley. I'd like to thank them for being here today. So, BL Tech is a local engineering company that was founded by the brothers Mark and Shane Hugel in 2011, and the company specializes in designing airsoft sound simulators. Their main products are airsoft sound simulators in forms of guns and explosives. Most of their customers are from military backgrounds who use the product for training purposes for a more realistic experience. So some of their products are the M203 grenade launcher, and so the way they work is that they have two different parts, one for bullets firing and one for the sound, the ammunition, plastic projectiles, and powered by pressured gas, compressed gas. The second part of the design generates a gunshot sound, and the way this works, okay, I think I'm just going to leave it here. And the ignition system, we should cut that bit out as well. So this is the two products that they're building at the moment. Okay, so I have to exit those videos later. So our project specifications, and I'll hand it to Bana. Yep. Hello, I'm Bana Benjamin. So our project specification. The problem is that BLTech does not know the minimum voltage and energy required to ignite propane within the chamber. So our project is to design a high voltage ignition system that allows the energy and voltage to be simply varied. And then we're going to undertake investigative tests to determine the optimal the optimal energy and voltage required to ignite propane. So our project parameters is output sound should create a spark. Output should create a spark that will ignite propane, resulting in a satisfied gunfire sound. The output energy should be variable up to 50 joules, and the output voltage variable up to 30 kilovolts. Time at which the spark is generated must be able to controlled. So the breakdown voltage of air is 3 kilovolts per millimeter. So we have to design a high voltage converter that can give an output of 3 kilovolts and higher. So the way ignition works is that it requires a certain amount of energy and heat. So different chemicals require a different amount of energy to ignite and combust. To ignite a reaction, certain energy needs to be supplied to the system called initiation energy. After it reaches the activation energy, the combustion can happen. So the fuel we're using is propane, and it roughly requires about 170 kilojoules per mole to combust, providing 50 megajoules per mole after the combustion, making it a very effective fuel, which is why we're using this. But the behavior of the propane is that its percentage of it to air where it does combust is from 2.1% to somewhere around 9.5 to 10.1%. These are called the lower explosive limit and the upper explosive limit. If the percentage in air is below 2.1%, there's not enough propane to be ignited, and if it's above 9.5 to 10.1, there's not enough oxygen and the system chokes. So we did some calculations with propane combustion. One of the ones we looked at was the actual chemical transformation through the combustion, and we found that the ratio that gives optimum combustion is about 5.8% propane to air and volume. In this percentage, no propane or oxygen will be wasted, and it will be a result in a full combustion. And now I'm going to hand it over to Peter, who's going to talk about combustions. Thank you. So, about combustions, there's two different types of combustions: laminar combustion and turbulent combustion. What we did was we did some experiments using a voltage arc coming out of a transformer, and we found that laminar combustion occurred. What that is that it is a slow burn, and that didn't work. So this is how the system works. So we have air coming out from the bottom through a orifice or valve, and then the spark ignites it. So with the spark that we used, the arc that we used before with the slow burn, it caused expansion, but then as soon as this system becomes an open system, further expansion escapes into the atmosphere, and we lose all the potential. So the valve did not shoot out very fast, therefore the striking sound that it should generate didn't occur. So what we need is a turbulent combustion, which is an instantaneous combustion, and to achieve that we need all of, or most of the propane in there to combust at a very short time before the system becomes open. So we did some calculations with the 5.8% volume percentage propane to air for optimum, and using dimensions in there, we managed to find that the combustion energy that we need for that much propane is about 7.17 joules. Now I'm going to pass it on to Anisha, who's going to talk about our simulation.
Hi everyone. So today so what we did is that we tried to think of a way to store all the energy and then releasing it in one fast go. And what we did was we made a Marx generator. The Marx generator, the way it works is that we have all of these capacitors in parallel, and then we supply a large DC voltage across it, so they all charge at the same time. And then what these are spark gaps. And the way they work is that they are open circuit, but once the voltage across the capacitors is reached, these spark gaps break down and short in a form of a spark, which then creates a short circuit across all of the capacitors in series, which then all of the resistors, in comparison to the spark flow, becomes really large and basically becomes an open circuit. So then all of the capacitors discharge really fast in series, resulting in a very large energy spark. And with our design, we managed to get about 5.56 joules out in the final spark. And of course, it can be bigger, but we're a little bit limited with what resources we have. Now this circuit, the spark plug, can actually be replaced using these gas discharge tubes. And because by controlling what gas is in there and the size of it, we can control exactly what voltage they break down. And we did some experiments with that, and they seem to work. So before we built it, we went through a simulation, and because our simulation do not have spark gaps, what we did was that we timed the charging of the capacitors, and then we used switches to switch the capacitors from being parallel to series and discharge, and then opening all the circuits, connecting all the resistors, so this way we can get them to charge in parallel and then discharge in series. And from our results that we got, it seems to work. We have them charging 1000 volts each across each capacitor, which is what we put in the input of the simulation. We got 4000 voltage out, 400 amps, very, very large, which is what we're expecting. So here is here's our test unit with spark, and you can see that across when they charge up, it's exactly how we expected with a large voltage discharge, and it works fairly well. So we connect it out to the test unit with the chamber and see how well it worked. You can see that it works fairly well. So next step is to design a circuit where we can actually tune the voltage and the energy. So this is a circuit that we use. What it does is that we use through a variac, we change the voltage going into the circuit, and then it gets rectified, and then using the same concept as Marx generator, we're charging up a capacitor, this time on the primary side, and then we discharge the capacitor
using a firing circuit, basically a switch, to discharge the capacitor really quick across the transformer, resulting in a large spark at the end. So we made this circuit and we gave it a try and see how it works. See that the spark was pretty good, and notice the waveform when that happened. The spark it gave out was pretty hot and scorched the table, so we're ready to do some testing. So we measured the energy in the spark and we captured it. It's very interesting over here that the voltage builds up until it's a high resistance, until the breakdown voltage is achieved, and then it clashes very suddenly because of a short circuit where the voltage drops and the current shoots up in the spark and slowly decays, and this is called the discharge time. And the total energy in there is about 5 joules in that spark. So this is the setup for the final testing with everything connected. The next part is to control how much gas we put in there, because at the moment we don't really know how much gas we're putting in. What we know is that the pressure inside the chamber, and also the valve size, and we need to, and how long we can open that for. So the way we did this is that we used the idea of this being a leak in a gas cylinder, and we use this assumption where the valve is in this sort of diameter or dimensions, and using that friction coefficient, we did some calculations using Bernoulli and all those other equations, gas exchange, and we found that when we have the valve open for 20 milliseconds, we get a 5.8% fuel to air percentage, and which is what we want for optimum burning. So with our test results, we found that with the test circuit we have 25 DC voltage. DC voltage is all we need. And with it, here is a video of our final result. And this is good because this low voltage putting across the capacitor opens up to possibilities of all the kinds of capacitances, which we can do further testing with. So in conclusion, we have in fact designed an electric ignition system, and has been designed for where the voltage and energy levels can be easily changed, and this will allow us to go in depth with our investigation so that we can find optimal combinations of the size of the spark gap, the gas level that we put in, and also the voltage and energy levels that we use. And for future work, it can include the development of this circuit in terms of the cost and the size, since it needs to fit in the gun, and also this design will be based on the parameters we get from all these testing. Thank you very much. Hope you enjoyed our presentation.